Okay. Hello, everyone. Thanks for the opportunity to share our research here that we conducted at KU Leuven in the context of streamflow estimation and Sentinel-1. So I'm presenting work of the remote sensing and data assimilation group of Gabrielle de Lannoy, and I want to explicitly thank all the external collaborators involved in this work that I show. I want to open my presentation with figures from the recent perspective paper on land surface data assimilation by Gabrielle de Lannoy and co-authors, which shows the development here that the land surface data assimilation is currently facing. We have more and more complex land surface models that represent more processes and interactions between these processes. At the same time, we have more and more land surface data available from satellites and other missions. So we are heading towards higher resolutions and more variables in our data assimilation schemes. And in this presentation, I want to address those developments by using Sentinel-1 data at a high resolution and by updating different variables at the same time and looking at different variables in the output. So Sentinel-1 is going to be the observation that used here in that talk. For those that are not so familiar with it, it's a constellation of two satellites. The first one was launched in 2014, the second in 2016. Unfortunately, the second one already died end of 2021. There are follow-ons scheduled, so it's a good mission for operational usage. We are using here in the presentation the interferometric white spot data aggregated to 1 kilometer resolution. And over Europe, we have a temporal coverage of 2 to 3 days. And yeah, Sentinel-1 is C-band, and we have over land vertical and vertical horizontal polarization. So we all know that C-band is sensitive to dynamics of the vegetation and the soil moisture, as illustrated here. So we have a long-term phenological cycle signal affecting the total backscatter, as well as short-term and long-term dynamics of the soil moisture. C-band is also sensitive to the dynamics of snow depths, which was shown more recently by works of Hans Lievens. Here showing a snow depth retrieval over the Alps. So regarding streamflow, well, that these two different information that we can get from Sentinel-1, there's a potential, of course, to improve streamflow estimates, either by directly updating soil moisture, because soil moisture controls the partitioning of rainfall into surface runoff and infiltration, and then causes also or controls the deeper infiltration and the base flow process. Assimilating backscatter can also be used to update vegetation, and this will affect transpiration. We can detect stress, and this has the potential to get updates of root zone moisture via the vegetation signal. And it can also help in getting the interception processes better, to have a better vegetation state. And snow depths, yeah, of course, also here we, by changing the snow depths in the data assimilation, we essentially correct for meteorological forcing errors, and a better snow depths will give improve the stream flow through better snowmelt masses in the snowmelt season. So in the first part, in the longer part of my presentation, I'm going to talk about the backscatter data assimilation to update soil moisture and vegetation and the impact on stream flow of that approach. That's a paper that's in review currently in Journal of Hydrometeorology. So this is the data assimilation scheme that we recently realized in the Land Information System of NASA. So we assimilate level 1 backscatter data of Sentinel-1. So on the right, you have the scheme. So we implemented that for the NOAA-MP land surface model that is coupled to a routing scheme the HiMap model. From that land model, we get the surface moisture and the leaf area index, which are both prognostic variables. So it's a dynamic vegetation model. This goes into our observation operator, the water cloud model that gives us predictions of backscatter that go into the one-dimensional Salmon-Kalman filter that we are using. And those innovations are then used to update soil moisture in different layers and leaf area index. We implemented different options. So either we assimilate only VV or jointly VV and VH. And either we update only surface moisture or both simultaneously. So what we implement or what we used in our experiments is model and observations at 1 kilometer resolution. And the first paper used that approach for irrigation detection and data assimilation over irrigation. And in the talk today, I'm going to show the impact on stream flow. So a few words about the observation operator. So it's a water cloud model. It's a very simplified model, a backscatter model. It has only 4 parameters, 2 parameters for simulating the soil backscatter and 2 parameters related to the vegetation. So simulating the attenuation of the vegetation and the volume scattering of the vegetation. You see here on the right an example for one grid cell, because we calibrate the water cloud model for each grid cell to remove the bias. We don't do any further CDF matching. So that is our bias removal based on a Bayesian objective function. So you see here an illustration of the water cloud model. You see here different soil moistures. You basically see the linear relationship that is assumed in the water cloud model. Backscatter increases with soil moisture, and then you see here on the x-axis how leaf area index attenuates and becomes how volume scattering becomes dominant right of the dotted line here. So as perturbations, that's quite standard. We perturb forcing variables, rainfall, radiations, and then we perturb the states, surface soil moisture, and leaf area index. And as backscatter observation error, we assume 0.7 decibel. Those settings resulted in a unit standard deviation of the normalized observation minus forecast residuals. So we optimized our system with that metric. So we used that scheme in detail, investigated that scheme in detail over 2 catchments in Belgium, the Dema and the Oud catchment. And they have contrasting properties. So you see the northern one, the Dema catchment, is low topography, flat, and the Oud catchment has a higher topography. And the land use is also different here. On the bottom right, you see that the Dema catchment is dominated by croplands, and the Oud catchment is mainly dominated by forests. You see also that there is some variation of soil texture in the Dema catchment, while the Oud catchment has sandy loam. So you see also rain gauges that we used to estimate the precipitation error. So our model was driven by MERA2 rain gauge corrected data, but those rain gauges are not used for correction. They are only available here at the national level. And we used those to estimate the precipitation error. And then we have stream gauges that we used to evaluate our stream flow in the open loop and the data assimilation. So our study period is 2015 to 2021, covering the Sentinel-1 period. Here are results of the observation minus forecast residuals. For VV, the patterns look very similar for VH. And you see also the standard deviation of the surface soil moisture increments and the leaf area index increments. And you can see that the patterns in both innovations and the increments correlate with land use patterns. We have clearly highest O-F residuals and increments over the croplands. We looked into the surface soil moisture increments and how they relate to precipitation errors of the previous day. And you can see that for the higher precipitation errors, the increments do correct to some extent. So that is a good reference to check whether we are improving soil moisture. And another evaluation we did was against independent soil moisture retrievals. And here we used the SMAP level 2 retrievals, the enhanced product 9 kilometer resolution. And you can see here on the left the correlation between the open loop and the SMAP soil moisture, and then between data assimilation and SMAP, and then here is the difference. And you can see that we improve the correlation with that independent soil moisture retrieval. And you can also see that we have mainly improvements over the croplands, where we had the largest innovations and increments. The results for leaf area index looked quite differently. There, we don't see an improvement when we compare it with the Copernicus Global Land Cover Surface leaf area data. And this is the case regardless of whether we update leaf area index here on the right or whether we don't update leaf area index. So by only updating soil moisture, we get a degradation relative to that leaf area index product. And this doesn't improve when we directly update leaf area index. And I think can you still hear me? There was some connection problem, I think.
Yeah, you?
Okay. Okay, so that degradation leaf area index I want to illustrate here in a time series. So you see here the DEMA catchment averaged time series of surface soil moisture, root zone soil moisture, and leaf area index. And in the black, with the black dots, you see in the top as a SMAP soil moisture retrieval reference, and here at the bottom, it's the leaf area index reference. And in blue and red, you see open loop and data assimilation. You can see that by assimilating backscatter, we get closer to the SMAP reference data in the spring when the SMAP data also indicates a drying, which is not in the open loop. And you can see that this has a strong impact on the modeled leaf area index, and that this is actually causing the major part of our degradation that we see. So soil moisture is lowered and decreases leaf area index, so lowers the vegetation growth, but that's actually not in the reference data. So LAI updating did not correct for it, as I said, so that these time series look very similar for the soil moisture only updating case and for the simultaneous updating. So one thing that we found in NOAMP is that there is a strong intrinsic model equilibrium state in the vegetation model of NOAMP, which we have a drift back to the equilibrium state after updating, and this makes that model quite rigid against vegetation updating. The other thing that we don't see an improvement is that we assume leaf area index in our water cloud model to be a good vegetation descriptor, but of course we would rather need a vegetation optical depth and vegetation water content. So discrepancies may come from there also. Let's look at the impact on stream flow. So for the Urt catchment average, here an example where the data assimilation had a positive impact. So you see here the surface moisture in the middle of the open loop and also the stream flow of the open loop. On the left, the observations, on the right, the data assimilation. And we identified events in our time series based on the observations, 6-day periods with a clear precipitation event in the beginning and then no precipitation. And we can see that a small increase in surface soil moisture and also root zone soil moisture due to data assimilation increases the stream flow towards the level, towards the observed data. Still, it comes from a very biased state for that period because precipitation was underestimated in the previous months or previous months before, and the data is partly correct for it. When we compare that systematically for all events, so that is an event-based evaluation, Q mod against the Q ops, correlation for total stream flow and the storm flow only part, we see that we systematically improve for the Urt catchment, the events for both experiments, only updating soil moisture or soil moisture and leaf area index. But for the demo, we barely see any impact. And this is quite unexpected because you remember from the beginning that the Urt catchment is a forested catchment. So we didn't expect that C-band backscatter is performing well over that canopy. And the other reason is we saw the biggest improvement against SMAP surface soil moisture for the DEMA, for the cropland area actually, which is also less. But we found that the properties of the two catchments are very different. So we have a much stronger soil moisture to runoff coupling over the Urt. And we evaluated that by looking at the correlation between the surface soil moisture and the runoff coefficient. So the ratio of stream flow over precipitation. And you can see that so for the model and for the observations, orange and black, the DEMA has a much lower coupling between soil moisture and runoff than the Urt. And we can, simply based on these different characteristics of the two catchments, we can expect already less impact of soil moisture data assimilation on stream flow over the DEMA compared to the Urt. Quickly, on the potential to improve stream flow by snow depth data assimilation. So that's the paper that is Brangers preparing, and that is only 2 slides, so I will come to my end. So snow depth data assimilation, that's a study area in the Alps. We have several snow depth stations that were used for evaluation and stream flow stations. And you can see here the observations. So the Sentinel-1 based snow depth retrieval on the left, the open loop where we see that snow depth is underestimated and the data assimilation brings it closer to the observations. She also worked with NoMP. On the modeling side, she used the best possible options, so rain gauge corrected and lapse rate correction. When comparing those snow depths from the analysis with in situ data, one can see that mainly the bias improves while correlation and mean absolute error is rather unaffected. And now the impact on stream flow. So with that bias reduction over those many stations, she found that Sentinel-1 snow depth data assimilation improves stream flow for correlation and also the other metrics. A quick outlook. So we want to combine the snow depth data assimilation and the backscatter data assimilation with soil moisture and vegetation updating over the Po River Valley, where we also look into the effect of irrigation on the water cycle. So water is extracted from rivers, so affects the water cycle on the land and changes rivers. So in that project, we want to integrate what I've showed before to analyze the effect on stream flow in the Po River Valley. Conclusions, wrapping up everything. So the backscatter DA for soil moisture and leaf area index at high resolution, 1 kilometer here, improved the soil moisture, and that also improved the stream flow when we look at the catchment with a strong soil moisture runoff coupling. The dynamic vegetation model is crucial, and to get also improvement for vegetation, and we haven't found them. So one thing is that we actually saw that an improved soil moisture did not improve leaf area index. The other thing is that we had this strong post-updated drift of the NOIMP model, and both suggests that parameter updating instead of state updating is research that should be conducted. Then the second part, I showed that snow Sentinel-1 retrievals, so snow depth retrievals from Sentinel-1 can improve stream flow via the reduction in the bias of the snow depths. And I would like to thank the funding sources and thank you for listening, and happy to take questions.
Thank you very much, Michel. So nice to see these very promising results with Sentinel-1 data assimilation. I'm looking at the chat. So Sophia, you want to ask your question, Sophia? Oh.
Yeah, I was just wondering if you could speak to, if you know what it would take to make the NOIMP soil moisture leaf area index relationship less rigid, if you have any insights into that.
Sorry, what to get what less rigid? The vegetation or the soil moisture? Because the soil moisture was not rigid.
Yeah, the relationship between the soil moisture and the leaf area index.
Yeah, I think the phenological model of NOIMP uses a strong equilibrium state, and that I think that needs conceptually needs to be changed. We also work with Sentinel-1 backscatter data assimilation using the aquacrop, a crop growth model. So the aquacrop from FAO, and that is behaving differently. That doesn't work with an equilibrium state, and when vegetation is updated in that model, the model simply continues from there to grow based on the conditions. There's no drift back. I think that is how I would approach to make it less rigid.
Thank you. Do we have time for more questions? I'm asking to Sophia and Lars. I'm watching the clock. Well, if we have time for one more, I was wondering, Michel, if in your coupled model between NOIMP and IMAP, is it a one-way coupling or two ways? Does your soil moisture influences river routing, but does the river system influence soil moisture?
Yeah, it has the option to model two-way interaction.
Okay.
But we haven't used it, and I'm not sure how relevant it is for our streams in those two catchments. But yeah, it would be interesting maybe to look at it, but it's not considered in the forward model.
Okay.
The model, yeah.
And if we have time for one more, maybe. So in the impact on the river flow that you are showing, it's always related to deficiencies in the forcing, lack of precipitation when you looked at soil moisture, or underestimation of snow when you looked at snow. So it improves the river discharge. But I was wondering what happens when your data assimilation system corrects for issues in the processes, like for example, snow melt issues, and how it would impact the river discharge in this case. When you have negative increments and when you extract water from the system, do you think it can have a negative impact on river discharge in this case?
I think I didn't get fully the questions.
When you have positive increments because you
Yes.
underestimated snow or underestimated soil moisture,
Yes.
you bring more. You had an underestimation of the river discharge, so adding positive increment in snow or soil moisture improves. But when you have negative increments, let's say if you had a model which is melting snow too slowly, you would remove snow from the system. it would just disappear and not be available for the river discharge. So how would you cope with this?
Okay, I see. Yeah, for the snow depth data assimilation, at the moment, the Sentinel-1 based snow depth retrievals are flagged for wet snow conditions. So in fact, we only assimilate the accumulation of snow.
Okay.
So the accumulation phase. So actually, yeah, but if we're going to assimilate also the melting period, it will be a problem indeed. It's a very good question. I'm not sure how to handle that.
Okay, yeah, it's
Yeah.
something maybe we can discuss further.
Yeah, very good.
Thank you very much. So we can close the session, I think. Thanks to all the speakers for their presentations and for the great questions as well from the audience. So thanks to all.